So I want to talk today about after Meltdown and Spectre. So we'll split the talk into a couple of sections. We'll talk a little bit about what happened, and then we'll talk a little bit about where we go from here. And then there's time at the end for some questions. Okay. So we have a logo fest of the various vulnerabilities that were announced last year. These days, if you want to be successful in publishing papers, it's very important to have a logo and a cute name. These particular issues often target one or two vendors in particular, but I want to say up front that this is not about any one vendor. Everybody in the industry was impacted by these to differing extents, but it's really about challenges we face as an industry, right? So I'm not singling anybody out today. That said, over the past year, here's the list of some of the different microarchitecture side channel vulnerabilities that we've had to deal with. We'll get to all of them later in the talk. Why did this happen? Well, this is my personal take on it. I think we had decades of unreasonable expectations. And what I mean there is, my background is software, right? So I'm used to just every year, every 2 years, getting a computer that's faster and does more stuff, right? I don't have to improve my code. I don't have to refactor it. I don't have to learn to write better code. You guys just make better hardware, and we don't ask you how or why, right? So everybody is to blame to different extents here. It's not about the hardware guys screwing up, and we'll talk more toward the end about how it is about a need for software and hardware folks to communicate more together as we build new designs. But you can see from Hennessy and Patterson, the first figure in their computer architecture book shows the growth in IPC that we had over preceding decades. And in the past few years, that's been slowing down. We've all heard about Moore's Law coming to an end. And yet every year, we're still trying to get more and more performance, right? So a lot of these vulnerabilities come from the trade-offs that happen between performance versus security versus other constraints in a design. And very few users have put their hands up and said, my most important thing is that you build me the most secure design possible. Of course it's important, but if you asked a couple of years ago, what do people want? It's always performance. It's spec, it's performance, performance, performance. So let's talk about the background to these issues. This is kind of a very quick walk through various computer architecture topics. So we're going to talk about instruction set architectures today, which, as a reminder, is describing the contract that we software folks have with the hardware. If we program to these interfaces, then our program will run across compatible machines that implement that instruction set architecture. And we have different states inside machines that implement ISAs. We have application software, we have operating system software that manages the machine, and we have these different privilege levels that separate what the operating system is doing from individual applications. What a programmer is doing is they're writing normally in a high-level language. That code is getting compiled, and ultimately what is being emitted is machine code that targets that particular ISA. Traditionally, these have been timing independent, right? I run this code. It's not embedded in my program how that will perform. It's up to a particular hardware, a particular platform to execute that code, and one machine may perform differently from another. But one of the problems we're going to see today is that the design of these machines, the design of these ISAs, is done in a timing-independent fashion. So application programs, we use non-privileged instructions in our programs to perform various calculations. While a program is executing, we call that a process, and it has various state. It has registers that embody the particular calculations as they're happening, and we also have memory as we load and store values that we're working on, and we have a virtual memory abstraction that we use in which your application thinks it has, almost unlimited amounts of memory, and underneath, the operating system is using various interfaces to provide this abstraction and manage it. Programs request services from the operating system using defined interfaces. And some applications could have different subcontexts. One of the challenges we're going to find today is that it's not the case that you have sort of program A and program B here. It's more often the case that you have program A here and then program B. And inside program B, it's also doing B1.1, B1.2, and so on. For example, if you're running a web browser, inside your web browser, there's all different pieces of JavaScript being executed in there to serve ads and other content. So operating systems used privilege instructions to manage the application environment, and the operating system is responsible for switching between applications. It also manages the state, including the page tables that provide for the virtual memory abstraction. As we get closer to the hardware, programmers often think of processors. What they really mean are cores. We'll hear more about different cores today, of course. Some cores are multi-threaded. That means that within that core, resources are actually shared, and we provide for what we call, for example, logical processors. The operating system thinks these are independent entities, but they're actually sharing resources within the processor. And cores are tightly integrated into today's system-on-chip designs. As we get closer and closer to the actual calculations that are happening, we talk about kind of how far we are from memory. So we have external interfaces, we have external memory interfaces on this chip. We have different levels of memory as we get closer to the calculations. And what happens is data that we're working on flows through from the outside of the processor, flows through a cache hierarchy that caches, that stores copies of data that we're working on. And as we get closer and closer to the actual core that's doing the work, we have a very small cache inside that core, the level 1 cache, which is, again, one of the focuses of the vulnerabilities we're going to talk about today. We also have multiple sockets. There's a lot more complexity to how real systems are built. Okay, so microarchitecture is about the specific implementation of an architecture, right? We often talk about in-order or out-of-order designs. Let's look a little bit at those. So in a classical in-order core that you might see, for example, in a microcontroller or some embedded design, you have kind of your classic 5-stage fetch an instruction I'm going to execute, decode it, work out what it does, execute that instruction, and then write back the results to memory. It's a classical design everybody studies in school. And the thing about an in-order design is it's very simple. But it's not as performant as we've come to expect in servers and laptops and other devices. So what we can do is we can look at our programs, and we can look at the data that they're operating on, and we can realize that there's actually independent sets of operations. So we can turn our in-order program that does one thing followed by another into an out-of-order representation within the processor by separating based on data dependencies. So you can see here, I'm loading two values, I'm adding them together, and then I'm loading two values and adding them together. This is what my program's doing on the left, but inside the processor, I could realize that these are independent operations. And what we do inside modern processors is we have these large structures. We track the different operations we're going to perform based on their data dependencies. And we take our program, the program is expecting to run in order, we may execute it out of order, and then we retire or complete the individual operations back in order. So the programmer isn't necessarily aware that this has happened. And we have various complexity in modern out-of-order cores to take our program from the in-order front end and execute it using what's called an out-of-order back end. We may have further constraints, for example, on x86 architectures with things like memory ordering. We have to very carefully make sure that accesses to memory are sequenced to preserve the sequential consistency that we're expecting. So let's talk about some of the speculation structures that we have in modern processors. Start with basic directional branch prediction. We have a condition in a program that says, you know, is it raining today? Yes or no, right? The value of that variable, raining, may be immediately available to us. It may be close to the processor. It may be in the processor's level 1 cache. If it is, we can very quickly resolve this branch and work out whether the answer is true or false. If it's sitting in an external memory chip off a DDR interface, it may take some time for that data to be fetched and for us to determine which way this branch needs to go, so-called resolving the branch. So instead of sitting there and waiting to find out, we can predict ahead of time based on history. You know, every time I did this in the past, I'll skip to, yeah. Every time I did this in the past, I went this particular way. It was true. So guess next time that's the case. That's conditional branch prediction. And when we make these predictions, what we do is we enter a state inside the processor, a speculative state. So I'm guessing what's going to happen, but until I resolve this branch, I don't know. So I'm going to track everything I do after that, but I'm going to track it in a way that lets me throw it away if it turns out that that branch prediction was incorrect. Okay, so we have conditional branches. We also have indirect branches. So I might have a piece of code that goes, you know, from one function, makes a call through a function pointer or some reference to another piece of code. I don't even know where that is in my program. It's going to take me some time to resolve the address of the function I'm going to call. So again, instead of waiting for us to determine which way that's going to go, I look at the history and I say, every time this instruction executed in the past, it went here, so I'm going to guess that that's going to happen again in the future. We have other predictors inside modern processors. We can also guess the return stack. So every time I call a function, you know, I call a function and I have another primitive in my ISA that says return from that function and come back to where I came from. What I can do inside the processor is I can track those, and I can say, I've called into this function, push it onto a hidden return stack buffer, and then every time I hit a return instruction that says come back from that, I can guess where it's going to go because I tracked it when it came in. So I can guess which way I'm going to return back from my function calls as well. It's another kind of branch predictor. As I said before, we also have virtual memory in our machines. So we're using this interface between the application and the operating system to perform various services. But what's actually happening, at least historically, is we have one flat, contiguous virtual memory inside our machine, virtual memory space, where lower addresses represent our applications. This is true in Linux. Other operating systems vary, but it's similar. And we have higher memory addresses that represent kernel memory, operating system memory. And when I perform system calls into the operating system, I can actually share and continue to use the same memory translations for performance. We have protections in place that are supposed to say, when I'm inside the operating system code, I'm allowed to use that memory at the top of the memory range. When I'm inside the application, I can't touch it, right? We have these page tables that manage the translations, and in the page table, we have permission bits that tell us what we can and can't access based on the state that we're in. Okay, and as I said, page tables basically handle the translation from virtual memory addresses to the underlying physical memory. There's one set of page tables per application, and then there are common mappings for the operating system structures that every process sees. We also have other caches, if you like, inside the processor that store some of these translations for performance. So there's a concept called a translation look-aside buffer, a TLB, that caches the most recently used virtual to physical translations. And then during translation, there are various tricks that we perform. We split our memory address. We walk down through our page tables that handle the translation. They're hierarchical in nature. We can, in parallel, I'll actually go forward to caches. We can, in parallel with this translation, we can actually be starting to look up if we have the memory location we're trying to read in one of the processor caches. And there's a little trick we do here where we split the address. We're doing the translation from one part, walking through our page tables. We're taking the lower order part of that address, and we're starting to do the cache lookup in parallel. And that's a very common optimization. There may also be a second stage translation where we have a hypervisor in place. And so after we've done this, we do it again because the operating system thinks that it's running on bare metal, but that's really just an intermediate level, and the hypervisor is translating it again. Okay, so in a running system, historically at least, we would have a mix of data in our caches, in particular level 1 cache inside the processor. And some of that data may be secrets, maybe kernel secrets, maybe secrets from other processors. But because we have these memory translations in place, and the memory translations have associated privilege bits that say this is only available to this particular application level, we've had data that might be present in the cache, but an application is not supposed to be able to access that data.